Okay guys, this is section 2 of the capacitors. It's going to be short and sweet. It's very much about a practical endorsement experiment that we should be doing. We'll pick this up when we come back. So, circuits, capacitors in circuits, and it doesn't take a genius to work out, I'm sure, that actually it's all about the flow of charge, and what makes charge flow in a circuit is the battery. So we've basically got this idea of pumping charge around the circuit. It's not continuous, it's moving from one plate, leaving behind red charges here, like positiveness, as the charges get kicked off. And just like we had last year, Kirchhoff's laws state, show, explain and describe, whichever word you want to use, why charges end up where they do. Because the charges can only exist along one place or another. So as they come around, they're going to split, they're going to rejoin together, they're going to carry on. But any that are trapped in this gap here will only exist between this plate and these plates, because there's nowhere else for them to go, because you've got insulation in the gaps. You've got gaps in circuits. Okay, let's look at it. It's the idea is nice and straightforwardish. As I say, it's really thinking about the basics, and if we use the basis of what you did last year, you can be expected to derive the equations for this year. So, capacitors in circuits, we have series, we have parallel, and actually it's a bit easier to start with the parallel one. We can make an analogy to the equation that we had in section 1. We'll come back to that. But if we think about what's going on, if we want to think about the total charge that's flowing, okay, so if we talk about our charge as it flows through our battery, as it goes around, well, the charge must have come from these. So the charges that leave this side and therefore leave it positive, come through your cell, end up on the other side. The total charge that's going on to the circuit or through the circuit, so if I make a little t, subscript t for total, well, is going to be that charge and that charge, because as your electrons come in, they've got to go onto one plate or the other one. Okay, so Q1 plus Q2. Now, crucially, it's all back to that base equation, so Q equals CV, in which case what we can say is the capacitance of the full circuit comes from the full voltage, in other words, whatever we've got here, and it just adds up to the others. So C1 V1 plus C2 V2. Now, Kirchhoff's comes in because if we're thinking about that, it's a parallel circuit. We know that in parallel they've got the same potential difference. So V from the cell, let's call it V total, is V1 equals V2. So basically those come out to the same thing. So what we can end up with is, and I'll do it in 2 steps, we won't do it in the next one because it's a bit more complicated, but C total V equals C1 plus C2, put that in brackets, V. And so what do we got? Total capacitance is literally just the sum of the 2 or 3 or however many other capacitors you have. And if you think about it, it makes sense, because capacitance depends on area. Having 2 identical capacitors instead of 1 means basically you've got twice the area of plates. So again, it links in with that common sense approach to what capacitance is. The other one you could derive yourself. You know, freeze the video now, have a go. It's not a genius thing, it's just the same kind of complex, except in this circuit, in parallel, we know the currents add up. So in total, it's the charge that has moved round, so the charges add up. Whereas in this one, we've got a series circuit, so we know that the voltages add up in series. Okay, so we're going to start with the total voltage is V1 plus, V2. And so we can replace it just as we did before, and it all works through. So V is Q over C, so total charge over C total equals Q1 over C1 plus Q2 over C2. And so if we think about what's going on, then the charge that is flowed there, Q, is the same as the trapped charge that flows, is repelled off this plate and flows onto that plate, Q, which is the same as the charge that's repelled off this plate and goes round through the cell to the other side. So charge is the same everywhere. So in the same way I can simplify that. I'm just going to go straight to the answer as I say, QT equals Q1 equals Q2. So because they're the same, we can end up with 1 over C total equals 1 over C1 plus 1 over C2. So they got the same format as they did with resistors. Yeah, add them up, or it's reciprocals that are added up. Just notice it's the other way around. So this was series. It looks like the parallel equation for resistors. Parallel circuit looks like the series resistors equation. Okay, so it's the opposite way round because of that equation. Yeah, if that's our equivalent of I, the multiplier is on V rather than on the I side of the equation. Okay, so it has the opposite effect. That's basically it. That would be all you need to get into the experiment. Obviously there's a bit more to it than this, because we then start to think about what happens if you do have part parallel, part series circuits. Okay, so that gets a little bit more complicated, and the whole aim of the practical is start playing around with combinations to then try and get various values for capacitance and just see how that affects from voltage. Okay, how we measure it with voltage.